Hi, my name is Nhan. I'm data scientist at ITEMIS, and today I want to talk about deep probabilistic modeling, or in particular about probabilistic neural networks. And okay, deep neural networks currently represent state-of-the-art for many applications, starting from computer vision to text recognition, voice recognition, and then language modeling, for time series prediction and sequence prediction, in the field of healthcare and biology, but also in more complex systems with composed of many different sensors and input sources, like in autonomous driving and predictive maintenance. So deep neural networks are great. However, they have their limitations. So they need tons of labeled data. Tons of labeled data and a lot of computing power. Optimization is difficult and time-consuming, and no one really understands them. They are sensitive to adversarial attacks. Two examples for adversarial attacks are shown here. For instance, on the top example, one can construct a certain noise pattern, and if added to the original image, the neural network will misclassify, and this in a very confident way. And also here in the lower examples, even only one pixel was modified to make the neural network misclassify. Neural networks are sensitive to biases in the data set that can lead to racial and gender discrimination. I think on Monday in the keynote you have seen this picture already, the infamous Google case where two black people were misclassified as gorillas. The second example is actually a little bit funny. Here, this guy, the biometric passport photo checker of the website of, I think it was the New Zealand Department of Internal Affairs, rejected this poor guy's photo because it claims that his eyes were closed. Okay, in general, neural networks provide very poor representation of uncertainties. So, and what about uncertainties? Why do we care about, or why should we care about uncertainties? And I hope you all agree that informative decision-making requires an appropriate assessment of risks. And that means a proper uncertainty assessment of predictions. And this actually implies that many applications should crucially depend on the careful representation of uncertainty. Okay, think of messy environments where clean detection of objects are not possible. Or complex systems where safety is a real important issue. Or in the case of medical applications where the recommendation for the next treatment steps really depend on the critical assessment of risks and uncertainties of your predictions. Uncertainty can also provide expected variances, which enables you to plan more efficiently. But on the other hand, unexpected variances indicate anomalies. So that's where probabilistic approaches address this uncertainty problem. So it addresses these issues already mentioned with neural networks. The neural networks are often overconfident and represent uncertainties very poorly. So critical decisions should be based on robust uncertainty estimate. That means on well-calibrated uncertainties. And neural networks perform poorly on out-of-sample examples. And uncertainties can help at least to alleviate out-of-sample biases. Okay, here short review, short reminder of how a neural networks in general works. In general, neural networks are universal function approximators. They can, in theory, they can map any high-dimensional input to any target output, and deep neural networks consist of many layers of nonlinear functions with many parameters, often hundreds of thousands or millions. And optimizing these weights is using examples from your training data set is usually difficult and time-consuming. So, and neural networks return deterministic point estimates. So, but real-world problems usually are not deterministic. Even if you give them the same inputs, you often have a variation in the output. Yeah. And often it's a typical distribution in your target output. And the main reason for that is that even the most sophisticated model does not consider all variables. So there are hidden variables which your model does not consider. These are model uncertainties. And so the optimum would be to estimate the full target distribution. If that's not feasible, at least have a good estimate of the variance of that distribution, which can represent the uncertainty of your predictions. Okay, and some of you might think of Softmax, using the Softmax for classification. But Softmax for classification is kind of ad hoc. You put it just ad hoc on your system, and it turns out that they are often overconfident. I will show that also later for a few examples. Another aspect is sampling. So sampling from the real world is really hard. It's difficult. Even if you do a good job, it will never be perfect. And if you only consider point estimates, there's a high potential for biases. While if you estimate your interval estimates, you have a much better estimate on the uncertainties, and a better control on your robustness of your confidences. Okay, so probability is the math of reasoning under uncertainty. So one of the most fundamental theorems in probability theory is the Bayes rule. And I think the most intuitive way to derive the Bayes rule is to look at this image here. So let's consider two events that can occur, A and B, which can occur with a probability of PA and PB. And if we want to compute the joint probability that A and B happens at the same time, we can express that in terms of conditional probability. We can look from this side and say the probability probability of A conditioned on B, so that B happened, times the probability of B. But that's equal to, if you can see it, it's a symmetric problem. It's the same as if you look from the other side. It's the same as the probability of B conditioned on A times the probability of A. Yeah? And you just put this part here on the other side. So it's a very quick and intuitive way to derive it. So in probabilistic modeling, we infer probability distributions conditioned on the observed data. So we let A represent our model. So actually the parameters of our model, and represent B represents our data. So the goal is to get this to compute the posterior, which gives you the probability that your parameters are true of your model based on the data. Yeah, and for that we have to calculate these guys here, and they are called so. So important is that the parameters of your model are not treated as single values, but as distributions. So, and the prior distribution represents your prior knowledge of your problem. So, in case you have no idea, you are blank, you can use, for instance, a uniform distribution, which can represent your ignorance about that problem. In case you have some expert knowledge where you say, okay, this parameter can only be between 0 and 1 or something like that, you can use appropriate distribution, and that would then, in that case, act as a regulator. So the PB condition on A is the so-called likelihood. Here we reverse the problem. So we ask how probable is the data based on our model parameters. It sounds a little bit absurd, but actually you can calculate it. And PB is the probability of the data itself. It's in the context of the parameter space, and that's usually a normalization constant. It's a normalization constant where which involves integration of this part actually, and that's usually the hardest part to compute, because you often have distributions where the integrations are not tractable. So you have to do numerical approximations. So, and the posterior represents your updated model, or your updated model parameters based on the observed data. Okay, and these are all distributions. So maybe a small example here. Let's think, okay, let's say you want to estimate the weight or the mass of an aircraft, and your initial guess is 60 tons. Yeah? So, but you don't have a clue actually. But you're pretty sure it's not less than 30 tons. And you're pretty sure it's not more than 90 tons. So you choose let's say you use a Gaussian with a certain width. Then you do your measurements here and calculate the likelihoods. And the updated posterior usually gets narrower the more data you involve. So you get more confidence in it. Okay, a few examples. One simple example is probabilistic regression, where the models of your parameter are treated as distributions. In this case, Gaussians, and the output is target output is also Gaussians. And from the Gaussians, you can get the variance, and that can represent your uncertainty. Another example, Bayes networks is an example for a graphical probabilistic model where you model the conditional relations between certain systems of your model, certain states of your model. Sorry. Actually, it usually requires a high level of domain knowledge to generate accurate models. A more generic algorithm is Gaussian processes, where the idea is to fit superpositions of functions that are Gaussian distributed over the data. And they are usually, the optimization is slow, and especially with low data and high dimension. So it's really hard to scale these probabilistic models. So as a summary, so pros and cons of these probabilistic models, so they provide better calibration of uncertainties, usually require a moderate amount of data, and provide often better transparency. But the main issue is that they are really limited in scalability. And okay, development and implementing inference algorithms is difficult and time consuming. So the question is now, can we get the best of both worlds? So can we model uncertainties in neural networks? And there has been a lot of efforts in the research community in the recent years addressing this problem. And the two most popular methods are Monte Carlo dropout and the variation of weights. So in Monte Carlo dropout, you basically run dropout not only during training but also during testing or prediction. It's pretty straightforward to implement, and I will not talk about this in this talk, but you can look it up, for instance, here. So I will talk about the method of variational weights. Okay. Another reminder. So in neural networks, you basically apply a matrix multiplication of your input with the weights, which are single values, and then you add the bias weights. Yeah, these are single values you want to optimize. And to make it probabilistic in the weight variation method, I think you can guess, we have to replace the single values with distributions. And then we can sample from them to make our predictions. Okay. Building probabilistic models from scratch is difficult. It's really hard. But fortunately, there are tools and frameworks. They are so-called probabilistic programming languages. For example, PyMC, now in PyMC 3, it's been around for some time, and it's still very popular in the scientific community. Then there's Stan and Edward and Inference from Microsoft. Relatively new in the game is TensorFlow Probability. Actually, I think it integrated a version of Edward. And today I want to give you a few examples using Pyro, which is built on top of PyTorch. Okay, so Pyro, very similar to the other tools and frameworks. They provide high-level extractions to sample from many different probability distributions. It provides different Monte Carlo and variational inference methods. It supports GPU and is, as I said, built on top of PyTorch. Okay, and as the first example, I will, of course, show you the MNIST data set. I think most of you are very familiar with this data set. And with PyTorch, you can build a simple feed-forward layer with one hidden layer, like this. And it's relatively straightforward to get an accuracy of something like 98%. And I've done that. I trained the model and looked at the output of this Softmax. So on top of the output of the network, I applied the Softmax and looked at the response of these three relatively clean samples, images. So this is a tree, and very confidently you can see that the model is right for all of them. So then I picked a few messy samples. For instance, this 8. Okay, this 8 is not too messy. Even I could tell it's an 8, and also the model. I'm not sure if this is a 6, but also the model is a little bit less confident, but still very high. But actually, it's not correct, right? And here it's this is supposed to be a 5. It's not okay, but then I applied it on complete out-of-sample examples. So this is the fashion MNIST, has nothing to do with digits. And here, I think this response is acceptable, but you see that for many others, it's also confidently predicting things like this as a 3, I think. And it gets even worse if I use just random noise. Then it's still relatively confident that this is I think everything is an 8, right? In a way. So now I wanna convert our neural network into a probabilistic neural network. And for that, we can reuse the existing PyTorch module, neural network module, and then first we have to define the priors of all the weights, and we define them as Gaussians or as normal distributions with centered at 0 and with a sigma of 1. Yeah, we do that for all these all the weights of our full feed-forward neural network with one hidden layer. And then we put it into a dictionary and give it the same names as use the same naming scheme as in the PyTorch module, which is, if you don't remember, FC1 and out. Yeah? Oops. And then we convert it into a Pyro random module. So we lift it into a random module. That's how they call it. Yeah, and to be able to sample that neural network from the priors. And because it's a classification problem, we apply the Softmax, and then we pass it to the sampler along with the observed data. Okay. So remember, we want to get the posterior, compute the posterior from the likelihood and the prior, and we still have to do this one. And this is, as I said before, that's the most difficult part because it involves, if you have multi-dimensional distributions, you often don't have tractable integrations. And so exact Bayesian inference is not feasible very often for real world problems. The standard method in the past was Monte Carlo methods, but that is computationally really expensive. And there is now a variational inference method which scales much better than Monte Carlo methods. And the idea is to approximate the true distributions with a tractable one. And this next slide is a little bit technical, but I just sketch it. So for variation inference, we have an intractable distribution we want to approximate with a tractable one. In this case, it's again a Gaussian. And we need we use the so-called KL divergence as a measure for similarity between different distributions. And technically, it's actually part of equals the elbow plus a constant, and so that we have to. So that's called the evidence lower bound. That what we have to do at the end is minimize this elbow, just for the naming. And again using gradient descent as we know it with our networks, neural networks. Okay. And this variational inference is so we run a variational inference with the guide method. It looks a little bit a lot, but here what we do here is that we vary the parameters of the Gaussians, which is the mu and the sigma, with another Gaussian. Yeah. So we do this for all our parameters. And then we pass the model and the guide along with an optimizer and the loss function to this constructor of the stochastic variational inference constructor, and iterate over all data, where we calculate the loss and take a gradient step. Okay. The posterior now we can use to generate or to sample to generate many samples from it. For instance, here we sample 100 samples from the posterior, and then we can take the prediction of these from these sample models and apply a softmax, and for instance can use the mean of the response of the ensemble predictions as the output of our predictions, which I've shown here. Here on these are the same numbers and responses from the regular neural network. This is the one from the probabilistic neural network. So for the clean examples, it's a little bit less confident. But also for the messier examples, which how it's supposed to be, I think. But also for the out of sample examples. That's what you would expect from a good model, I think, and especially also for random noise. Yeah. So now I wanna show you a more practical example. It's an example from a predictive maintenance data set of 100 different aircraft turbine engines. This is publicly available on the NASA website. And so this data set contains time series data from 21 different sensors of these 100 different turbines. And here is, for example, a reading for one turbine. The readings of the first 10 sensors just before a failure. So here the failure happens, and this is the reading of the different sensors. And you might see some. Who does see some trend here? Yeah, there's probably some trend. But here are the next 11 to 21, also the next 11 sensor readings. Again, you might see some trends for some sensors. But of course, you can also run an LSTM on that. Probably for simplicity, I just ran a feed-forward neural network with 2 hidden layers, and then I predict the remaining usable lifetime. So this is basically the orange line here. So that is the number of, from the historical data, the number of days until some failure happens. Yeah? And this is the prediction of the neural network for each day. Actually, it's not bad, I think. It's okay. So predictions. It's not too bad. Now, I use the same neural network to lift it to a probabilistic neural network. So I do exactly the same as I've shown for the MNIST example. So then I run variational inference, and then as a result, I also sample 100 different models and get the mean, and also compute the standard deviation. Here indicated as the yellow margin, which corresponds to roughly a 95% confidence level. And this is the comparison. Between these two. And here's another example. A third one, and okay, actually I'm a little bit early, I have to say, but it's the last session anyways, and you're all tired, right? So, a summary. So deep neural networks currently represent state-of-the-art for many applications, from computer vision to forecasting. However, they have limitations, and we should not stop trying to improve them. So probabilistic models can help to obtain robust uncertainties, which helps to make more informative decisions. However, they scale very poorly. But I think probabilistic neural networks can be a way to combine the best from both philosophies. Thanks.